Hello students. Now we will discuss about the concept that how is a dipole affected when placed in a uniform electric field. That is electric dipole in a uniform electric field. What does it mean? There is a uniform electric field means the field at every point of the region or the space is same. The field intensity is uniform. Remember, this field is because of some external source. This field is not of the dipole, this is some external force field. So this is, say, a uniform electric field. Always a uniform electric field is represented by the parallel lines directed in the same direction. So this represents a uniform electric field E. In this field, we are placing an electric dipole, say AB. This is A and this is B. At A there is minus Q charge and at B there is plus Q charge. As usual, the length of the dipole is taken to be twice of A. This is its axis. We assume that this axis makes an angle theta with the direction of electric field. One more thing you can understand here, that there will be a dipole moment of this dipole which is directed from A to B. As we had discussed in the previous videos, the dipole moment is always from the negative charge to the positive charge. So this is vector P, the dipole moment from A to B. The angle of inclination we had taken as theta. Now the charge plus Q will have a force along the direction of field. When we discussed the concept of electric field, we had discussed that the force on a positive charge is along the direction of field and the force on a negative charge is opposite to the direction of field. So here on the charge plus Q, the force should be vector F, that is Q into E. Recall the concept when we discussed the physical meaning of electric field. So we had discussed this expression that F equals to Q naught vector E. So force is Q into E. Similarly, at point A, the force will come out to be F equals to minus QE. Why minus? The minus sign symbolizes or signifies that this force is directed opposite to the direction of electric field. The electric field is in this direction and the force is in this direction. One more thing you can recall and you can remember, that the direction of field shows that on this side it must have a positive charge and on this side it must have a negative charge. Any arbitrary charge can be there, but a direction of field, if it is directed in this direction, so definitely here will be a positive charge. So you can understand this as that the positive charge is repelling this positive charge and is attracting this negative charge. Okay, so this is the dipole force. Now these two forces, when are acting at the two ends of a straight rod or any body, so you can recall the concept of the force couple that we had discussed in the class 11th. What is a force couple? When two forces are equal in magnitude but directed oppositely. Equal in magnitude but directed oppositely, then they form a force couple. So here these two forces you can see are equal in magnitude. The force on plus Q charge, how much is that? This is plus QE, which we had represented as F, and the force on minus Q charge, this is also vector F, it is minus QE. To distinguish, you can write A and B, that is A and B. Sorry, this is B and this is A. You can see that the force A is equals to force B but directed opposite. So this confirms the conditions, the necessary requirements for a force couple to act. So these two forces are equal in magnitude but directed oppositely on the same body, then they will form the force couple. And remember, recall it, that every force couple has a tendency to rotate the body. Every force couple has a tendency to rotate the body. Recall the concept of the opening of the cap of a bottle, opening the taps. So what is there? We always are applying a force couple there. So similarly, this force couple has a tendency to rotate the dipole in this uniform electric field. Now furthermore, whenever there is a torque which is trying to rotate the body, so in rotational motion one more mathematical concept is very important, is very good, that is torque. So this dipole in this uniform field will experience a torque. So what we find out here? The torque on electric dipole. Now what is the expression for torque on electric dipole in terms of couple? Yes, very good. This is the either force, because the forces are equal in magnitude, their magnitudes are same. So either force, its value, its magnitude we are finding, multiplied to the arm of the couple. Remember, this is either force into arm of the couple. What is the arm of the couple? Arm of the couple is the perpendicular distance between two lines of action of the force. Arm of the couple is the perpendicular distance between two lines of actions of the force. So the torque is represented as tau, that equals to the force either A or B into arm of the couple. How do we find it out? From point A, we drop a perpendicular on the force FA. So FB drops a perpendicular on FA. So if it is A, it is B, let it be C. So BC is the arm of the couple. So we take that arm of the couple is BC. Now, this torque comes out to be F into this BC. In terms of this AB, we can identify this is perpendicular, this angle is theta, so this must also be theta. You can see these are corresponding angles. So if this is theta, this is 2A, this is BC, so this must be AB sine theta. Very good. It is AB sine theta. Now place the values. The torque comes out to be force. How much is that? Q into E. And AB is 2A sine theta. You can rearrange the terms as Q into 2A into E sine theta. Now Q into 2A, what is that? Very good. This is P, that is dipole moment of the dipole, and we have got its direction from A to B, from negative charge to positive charge. Good. So QA is P, so therefore torque comes out to be P E sine theta. So this is the expression for the torque experienced by a dipole placed in a uniform electric field. Remember that torque equals to Pe sine theta. Here dipole moment P is a vector quantity, E is a vector quantity. If we go again back to class 11, so we had got that AB sine theta, where A and B are vector magnitudes, then it equals to vector A cross vector B magnitude. Remember this? It means this is showing you a vector product, and we know with our study of 11th that torque is also a vector quantity. So in vector term, this torque can be taken as vector P cross vector E. This is that. So vector tau equals to vector P cross vector E, as these all three terms are in terms of vectors, and AB sin theta can be taken as vector A cross vector B as the study of 11th. Now we discuss here some special cases. What are they? The first special case is that if theta is 0 degree. What does it mean? That is, the dipole moment is placed in the field such that vector P is parallel to vector E. Okay, vector P is parallel to vector E. It means negative charge on this side, positive charge on this side, parallel to vector E. This gives us that sine theta equals to sine 0, and that comes out to be 0. Remember this, that the value of sine 0 degree is always 0. So therefore torque comes out to be Pe sine 0 simply 0. Means when it is placed along the direction of field, it experiences no torque. Similarly, if we consider that if theta is 180 degree, in that condition vector P is parallel to vector E but in opposite direction. So we term it that vector P is anti-parallel to vector E. What does it mean? That is, vector P is oppositely directed to vector E. It means that negative charge on this side and positive charge on this side. Remember that sine theta, that is sine 180, here is also 0. So therefore torque here is also 0. Means in both these conditions, whether parallel or anti-parallel, the torque will be 0. It means the torque it means that the dipole must not rotate as torque is 0. But there is a difference between the two terms. This is called as, it is stable equilibrium and this is unstable equilibrium. What do we term? What does it mean? It means that if the dipole is placed parallel to the vector E, then stability means that dipole, if deflected from its position, will try to sustain the same position. Here the net forces will be 0, but it tries to maintain its sustenance, its direction along the direction of vector E. This provides it stability. Deflected brings it back, slight deflection. But in this direction, in this formation, if it is directed opposite, then in that situation what happens? Vector P anti-parallel to E. So as soon as we deflect it, it completely rotates itself and aligns such that vector P becomes parallel to vector E. Again recall that when it is at this angle 180 degree, then this is unstable equilibrium, means if we deflect it here, so it rotates completely in search of alignment where vector P is parallel to vector E. So this is stable, it remains as it is. This is unstable, means if we deflect it, this completes it, take a rotation. So this is about the dipole in a uniform electric field. Now in continuation of this topic, let us discuss about the potential energy of an electric dipole. So the topic is potential energy of electric dipole. What does it mean? See, when we are rotating the dipole and when we have this torque acting on the dipole, then there will be some rotational motion. There can be a rotational motion from one certain angle to the other certain angle. And if there is the rotational motion, so there will be some energy stored in the dipole, which we term as the potential energy of electric dipole. So this is the energy possessed by the dipole in a uniform electric field, and this is on account of rotation caused because of torque. Very good. So let us consider that an electric dipole of dipole moment vector P placed in a uniform electric field vector E at an angle say theta 1 or say theta. So torque on dipole, that is tau equals to Pe sine theta. We just discussed this. This is torque equals to Pe sine theta. Now when this torque is acting on this, let the dipole is be rotated through an angle d theta. So a small work done. When we consider this rotational motion, so we will work out the work done in a small rotational motion. So if that rotational motion is through an angle d theta, so a small work done, that is, let it be dw, must be equal to what it should be. Yes, work done equals to force into displacement, and in rotational motion the work done is torque into angular displacement. Recall that at 11th class again, that torque is the rotational analog of force and angular displacement is the rotational analog of displacement. Okay, so this is torque, the rotational analog of force. So force into displacement is work. So here this will be torque into angular displacement. Now how much is torque? This is Pe sine theta d theta. Now let the dipole is rotated from theta 1 to theta 2. That is, initially the angle at which it was placed is theta 1, and finally when we are observing, then the angle is identified to be theta 2. So in that situation, the net work done, how to find it out? The net work done, that is W. We can recall that W can be observed or can be identified as integration of dW. Okay, now this integration of dW means integration of Pe sine theta d theta. Now here P is the dipole moment of the dipole, it is constant. For a given dipole, its dipole moment is constant, it does not vary. And E, we had taken uniform electric field, so E will also be constant, that is E. So you know that constants are not to be put inside the sign of integration. Secondly, we are integrating on the terms of angle theta, and theta is changing from theta 1 to theta 2. This provides us the limits of integration from theta 1 to theta 2. Initial angle theta 1, final angle theta 2. So in the next step what we do, that W can be taken as Pe out of the integration sign, because very good, they are constants. Integration of sine theta d theta from theta 1 to theta 2. Okay, now integration of sine theta is cos theta. Remember this, is it cos theta or what is that? Good, it is minus cos theta. Okay, so integration of sine theta is minus cos theta, so it is minus cos theta from theta 1 to theta 2. Okay, now this minus is to be taken outside, so this becomes W equals to minus Pe. And solving out these limits, how do we do that? Yes, upper limit minus lower limit, upper limit minus lower limit, that is the function with upper limit minus the function with lower limit. So it is cos theta 2 minus cos theta 1. Clear? So this is the work done. Now this work done gets stored in the dipole in the form of its potential energy. So therefore potential energy of the dipole, that is, U say we represent this, हम U का यूज करते हैं टू रिप्रेजेंट द पोटेंशियल एनर्जी. तो U is equal to the work done, that is minus PE cos theta 2 minus cos theta 1. This is this. Clear? This is the expression for the potential energy of electric dipole. Now its special cases. What is that? That first of all we consider that let theta 1 is 90 degree. That is, initially we place the dipole perpendicular to the electric field. Theta 1 is 90 means we place the dipole perpendicular to the electric field. From this expression of torque, if theta is 90, so sin 90 is 1 maximum value, so it will experience a maximum torque. So theta 1 is 90 degree and let theta 2 be theta. It stops ultimately at an angle theta. So therefore U comes out to be minus PE cos theta minus cos 90. Now as I told you, sin 90 is 1. How much is cos 90? Good, cos 90 is 0. So this becomes U equals to minus PE cos theta, or we can write it as minus P vector dot E vector. So this is the condition when the theta 1 is 90 and theta 2 is theta. The second condition we can have here is that let theta 1 is 0 degree and theta 2 is theta. How much will it be now? Initially we had kept it at how much angle? Good, 0 degree. So U comes out to be U comes out to be minus PE into cos theta minus cos 0 degree. Cos 0 degree is 1. This is cos theta. So this comes out to be minus PE into cos theta minus 1, or we can write U as PE into 1 minus cos theta. So these are the two special cases for the energy stored in a dipole. This is one of the important cases of this, because this is generally asked as a direct question in 1 mark or 2 marks. So this is all about this topic about the dipoles. So revise this chapter completely, revise the whole dipole completely, properly, and please subscribe to the channel. Thank you.